So, good morning, ladies and gentlemen. It is our pleasure to welcome you to the speech synthesis session with the title Speech Synthesis, Other Topics. And as you know, we have 4 presentations on the program. And so let's start with the first presentation, which will be given actually by my colleague here, Pucher. And the title of his presentation is Conversion of airborne to bone-conducted speech with deep neural networks. So, Michael, please.
Good morning. Welcome to my presentation. I'm happy to give here the first presentation at this first hybrid interspeech. Yes, I will present our work on conversion of airborne to bone-conducted speech. So first I will shortly discuss the background of this work and recording, then a little bit of analysis of the data and show how we did the conversion, and then an evaluation and conclusion. So the background is that we all know the alienating effect of self-speech. So when we hear our own speech in playback, and this is mainly due to the missing bone conduction signal. Of course, there are also additional things because we are physically speaking ourselves, but an important part is this missing bone conduction signal. And this alienating effect leads to a negative emotional reaction. And furthermore, it was also shown, actually, we investigated this, that when you hear to one's own airborne voice, then this can lead to better learning outcomes and higher success rates and endurance in blind children. This we evaluated with audiobooks. And also hearing the own voice is perceived as being more attractive, even when it's not recognized as the own voice. And for the bone conduction, it was also shown that several phonemes, like the nasals, and the close mid-vowel, this was used in this evaluation, have a high bone conducted relative to air-conducted sound transmission. And this means that a global filtering approach, as was proposed in previous work, is not sufficient to model this bone-conducted speech part. And yeah, this is how we did our recordings. So for the bone conduction recordings, we used an accelerometer, and then this accelerometer was like encapsulated in some thermoplastic, and this was then our bone conduction microphone, so to call. And we recorded 8 non-professional speakers of regional standard Austrian German, and the age ranged from 20 to 55, and we had 3 female and 5 male speakers. And here you can also see the recording setup. Actually, we also recorded in-ear speech and calibration signals, but this was not used for this investigation. So I just play you now the airborne speech.
Heute ist schönes Frühlingswetter.
It's not very loud actually. And then the bone-conducted speech. Yeah, you can maybe, yeah. I have further samples of the bone conduction later. Maybe we can hear it better. So if we look at the magnitude spectrogram of the different signals, we can see the airborne speech here and the airborne speech plus bone conduction here. And we see that the content is up to 8,000 hertz. And then we have the bone signal here in the lower left and the bone residual in the lower right. And we see there is not anything going above 2000 Hertz. And the bone signal, I mean, if you listen to the signal also on an earphone, you can hear that all the speech, all the phonetic content is there, so you can understand everything. And this you can also see in this magnitude spectrogram, but you can hardly see anything in this residual part. And if we draw a very simple system, how we could do, how we could describe this process and how we could use inverse filtering to reconstruct the bone signal. We could inverse filter the speech to get the excitation, and then have a bone conduction filter to reconstruct the bone signal. So if we draw a more realistic, complicated system diagram, then it would look like this, because we know that we have in the bone conduction, we have 3 different filters, so to say. We have in the inner and in the middle and in the outer ear. And these contribute differently to the bone conduction, partly via vibration and partly via acoustics also. And also the vocal tract needs to be modeled by multiple systems which are connected. However, from our recordings, we only have this bone conduction recording, where we put the microphone at the mastoid bone behind the ear, behind the right ear. And we have the airborne signals, so it's very hard to estimate all these subsystems. So what we do is we use a voice conversion approach where we train the system with the bone and the airborne speech, and then we convert the airborne speech to the bone signal, and then this converted signal is then added to the original airborne speech. So we do not have to change anything about the airborne speech signal, so there's no quality problem there. We also did an analysis using HMM, so decision trees for male capture, trained on the speech, the bone conduction, and this bone speech capstra. And we see that, these are the number of questions that are used in the decision trees, and this gives us a kind of indirect proof of the phonetic content in this residual part. And also when we look here at these are the comparison of this bone speech versus bone, and we see there's a large intersection of the used questions, and also in this difference. So this is the difference between bones questions that are used in bone speech and not in bone is very small. So seems to look good. And for the conversion, now we use this 8 speaker and 200 sentences we had from each speaker, and split into training, development, and test sentences. And so 2 systems were, they called here filter speak and filter all. So where we have a filter that applies one single transfer function to the entirety of the target speaker signal. So either it's trained speaker dependent or on all speaker signals. And the LSTM systems use a 2-layer bidirectional network with 256 units. And we use 55 malcapsular parameters and 5 band aperiodicity parameters. And they are converted then to the parameters, to the bone parameters of the same type. And the F0 is used from the source speaker. And then we also used a speaker embedding, a residual network-based classifier with an 8-dimensional embedding, and we used 51 background speakers from our database. So here now the different LSTM-based conversion systems. You cannot see it. Yeah, there are two systems that are with red backgrounds, this one and this one, which are especially interesting because they can be trained without having any bone conduction data from the target speaker. So this one here, we first train an average LSTM, then we do the adaptation, and then when we want to convert the speech of speaker B, then we find the most similar speaker to speaker B using our embedding, and then we use the model of this most similar speaker. And here we train this average voice with the embedding, and then we use, in the test case, we use the embedding and the speech of the speaker. Then we did an objective evaluation of these different systems, computing the Mel capsule distortion, shown here, and here are the different systems. And here you see this, these filter-based systems, and here are the LSTM-based systems. And actually the LSTM-based systems all outperform these filter-based systems. And here you also see the left bar always shows the all Mel capsule coefficients, and the right bar without the zeroth coefficient. So we see that the zeroth coefficient makes up quite some part of the error also. And again, here the these are three systems where no bone conduction data of the target speaker is needed. So we also have this field all system. This is all also trained in a way that we do not need bone conduction data of the target speaker with cross-validation. These are now the samples. Yeah. Sorry, it's...
Heute ist schönes Frühlingswetter. Heute ist schönes Frühlingswetter. Heute ist schönes Frühlingswetter. Heute ist schönes Frühlingswetter. Heute ist schönes Frühlingswetter.
So it's really difficult to partly spot the difference between the systems. And so we also did a subjective evaluation. And here we asked 11 listeners to judge which of the reconstructed signals is more similar to our recorded bone conduction signal. And here we used only the three systems that actually can be used without bone conduction from the target speaker. So these are this LSTM sim, embed, and this field all. And again, we see that these two LSTM-based systems outperform this filter, and this is also significantly. Okay, now I already come to my conclusion. So we have presented different systems for conversion from airborne to bone-conducted speech. And then, we showed the objective evaluation that the trained systems outperform these simple global filter-based systems. And in the subjective evaluation, where we only use the three systems that can be trained with bone-conducted speech from the target speaker, we also saw that the LSTM-based systems are better, like producing a signal that is closer to the recorded signal. So concerning the evaluation, what is still missing is, so we didn't evaluate with the speakers themselves. So it's the speakers that we have recorded. And this is, so this is a part of the evaluation that still has to be done, because the application is, would be in language learning, or for singing, or for any scenario where you want to have a more realistic rendering of the own voice for example, also if you want to select a voice that is similar to your own voice, you might also want to add this bone-conducted speech. And for this evaluation, it would be necessary that the speaker produces speech, maybe with a closed headphone, and then he or she can hear a signal and then has to judge if this is more or less similar to the thing that was heard when speaking. This is an evaluation that still has to be done. Okay, then, this was my presentation. Thank you for your attention.
Okay, thank you for the presentation. And we now have some time for questions. I just remind that we have several types of questions. Some questions could be, of course, from here, and some questions from the online environment. So please, questions, comments. So we have a question from the online. I'm supposed to read it, I think. So thanks, Michal, for the interesting talk. Did you some analysis to find more information about which aspects the LSTM is improving in relation to filter-based systems?
No, we didn't. We didn't do more analysis as the one that I actually showed. So I mean, we saw that this the signal has some. I mean, also previous studies showed that this kind of signal has some time-dependent or phone-dependent variation, and this kind of variation, I mean, it cannot be covered by this filter system because this is only one. It's only one transfer function that, like a low-pass filter on the speech signal, and so it cannot cover this time-dependent information, and this is covered by the LSTM, but we haven't looked into this in more detail.
Okay, thank you. I will check. There are no other questions from the online environment, so do we have any questions here? If not, I think we can thank the speaker again, and we can continue to the other presentation.